This is video 1.2. We're looking at state. Now this is still in the section here to do with matter, and our key concept is particles collide, and this explains a huge amount. So we've got to keep that idea in the forefront of our minds. So we met state a little bit in the last video, but we're looking at it in a little bit more detail. We've got here a graph showing us energy being supplied and the temperature going up, so the energy per particle is going up. Here it's a solid, here it's melting, so we've got a combination of solid and liquid. Here is some heating of the liquid, and here we have boiling of the liquid, so we've got it turning into a gas here, the third state there. Now a key contrast is the difference between melting and heating. So when something's being melted, the temperature doesn't change, slightly surprisingly, and we have this pause here. And if we want to know the energy that we need to melt something, we need to know the mass of the object and this number here, the specific latent heat. So this is a number that tells you how much energy you need to melt something. In a very similar way, we've got this formula here, and this tells us if we want to heat something up, we need to know what temperature change we want, the mass of the object, but also this thing here, this specific heat capacity. So that's a number that tells us how something heats up. Now finally over here we've got the idea of chemical change versus physical change, and the idea that one is reversible, i.e. physical change, easily reversible, chemical change isn't. So here we've got some state changes. You're quite familiar with these, I strongly suspect. So we've got an increase in temperature here, it melts, bigger volume, and even larger volume here. And we've got our various different terms here. The slightly more unusual ones are sublimation and deposition. But again, the key point is that the mass doesn't change. You can see in each of these squares, we've got the same number of atoms. Here we've got the idea of physical change. So here we've got our atoms here, and they're just arranged differently. We say they're a liquid, but essentially that's all that's happening. And so here we've got it being heated up, and as we all know, very quickly it turns back into a solid. Now that's in contrast to chemical change. So here we've got some oxygen, here we've got some carbon in gas form, and they combine to form carbon dioxide in this case. And they won't easily, naturally change back into the starting point. So that's the key thing. Reversible, physical, very easy reversible, chemical, pretty much one way only. Right, so the more unusual part are these two ideas, specific heat capacity and specific latent heat. So they, as I said before, they are numbers that tell you how something melts in the case of specific latent heat. So how much energy do you need to melt a kilogram of ice? It turns out to be this figure. If you want to heat up a kilogram of ice from -10 to -9, yeah, so that's an increase in temperature, it will be this much energy. So really key idea. We've got heating, so we're heating a solid, and here we're melting, and they're quite different processes. The energy is doing different things. Here the energy is breaking bonds. Here it's just adding to the kinetic energy of the particles. So it may be a weird idea, but ice does contain heat. So we're reinforcing that idea here. We've got more and more heat as the object increases, so from 5 or -5 to 0, then we have to supply more heat to do the melting, and then we add more energy. But all the way through, energy of the system is being added to. Now the difference between temperature and heat is quite a subtle one, so this is the analogy I've come up with. So a swimming pool actually has lots of energy in it. There's lots and lots of tons and tons of water. Over here a kettle doesn't have much water in it, but the molecules that are there individually have a lot more energy, and that's what temperature is. So temperature is energy per particle. So if I offered you 10 buckets with $20 notes in, or offered you a normal sized wallet with some $100 bills in, although per note there's more value here, more energy here, you'd actually go for this one because in total there's more energy. So in summary, temperature is energy per particle, or the value of a note, and heat is the total energy, which is the total money. So hopefully that makes the difference clear. So let's get back to this idea of specific heat capacity. So if you want to heat something, what do you need to know? How much of the substance have you got? What is the substance? And that's the tricky bit, the specific heat capacity. So specific to a subject, to a substance. It's to do with heat and how much heat can it hold, or how does it hold its heat, and how much hotter, what is the temperature change. And we turn that into a formula. So the energy required is the mass times the specific heat capacity. Yeah, so what is the substance times the temperature change. So here we see the effect of mass. Here we've got a big chunk of aluminium. We supply the same amount, so this particular point, let's say, same amount of energy. We've got a bigger M. C is the same in this case because we're dealing with aluminium, so we'll have a small temperature change. So here there'll be a small temperature change, or we can think of it as being over here. Here we've got less mass, so the temperature is going to go up. I mean, if we think of this more, if we had 100 tons of aluminium, the same amount of energy wouldn't change the temperature very much. Then we've got the effect of specific heat capacity. So now we're comparing aluminium again to copper. And copper has a much smaller specific heat capacity. So if the C is smaller, the delta T, the change in temperature, is going to be much greater for any particular energy supplied. Yeah, so energy is mass. The mass is the same in this example. Large specific heat capacity, small specific heat, and mathematically the temperature change is going to be larger. So here we've got a graph that shows us atomic number versus specific heat capacity. So you can see hydrogen, helium, very high specific heat capacities, and it tails off as we go along. So here's a worked example. Here we can see a tanker that's had an accident between one part of a foundry and another. So we've got 5 kilos, specific heat capacity is 100 joules per kilogram degree, 10 degree rise, so nice easy numbers. There's our formula, no need to rearrange it. So in this case we've got 5 times 100 times 10, 5,000. So we'd need 5,000 joules to heat up this 5 kilogram object. Finally then we've got the specific latent heat. So this is a huge iceberg, 5 times the size of London. It broke off in July 2017. So it's about 1 trillion tons. To melt 1 kilogram we need this much energy. So its energy is mass times latent heat, or specific latent heat. There is the calculation, and it would be about half the world's energy consumption for a year. Thank you for listening.